This is Andy Schweitzer, and first video in a series of videos involving states of matter. First question we'll pose here is, why is a salad a salad? And for this, we'll take a moment and just kind of look at a solid versus a liquid versus a gas. Then we're going to look at some internal and external factors that we can look at. So if you take a salad, you can easily just take a plate and you could stack a salad on top of it. We have particles that are, whether they're molecules, meaning they are covalently bound, or whether it's some sort of ionic formula unit, so covalent, versus if it's ionic, which means it's got some crystal structure that's a little more unique. All these particles in here are very much held together tightly. Okay? So if you were to blow a picture of that up, you'd see whether it's an ionic compound, whether it's covalent molecules, we have cations, anions, or we have some unit where there's a decent amount of attraction between these particles. Particles can, at this point, would be able to rotationally move in circle like this, but they would not be able to translationally move. So there is an intermolecular vibration that takes place between these particles, here. So they're always moving a little bit. So a solid, there is a large amount of force or of attraction between the particles. Okay. Now, for a liquid, we would need some sort of a dish here, all right? And in this case, particles, there's still a unique amount of attraction, all right? There's definitely attraction between particles, but now the particles can rotationally move and they can translationally move. So the term there is translational motion versus rotational motion. All right. So there is some attraction, just not as much. And then obviously for a gas, you would need to have some sort of container that's going to be able to hold a gas. Let's just say we have, it could even be a cup, whatever. Particles are flowing around in here, and they are free-flowing both translationally, bouncing off walls, and rotationally. So technically, is there any interaction between these guys? Well, we'll talk more about later, but essentially we're going to say at this point there are no forces of attraction or repulsion between these particles. Now, let's get back to solids. This little section is going to be dealing with solids. Okay. So let's look at some internal versus external forces, or let's say, I say factors, but I should say internal versus external factors. And you might use the word variable, for example. Okay. So, solids. Why is a solid a solid? Well, we have internal factors, and this is the way that I characterize it. I don't know that you would find all this content is in a books, internet. I'm just not quite so certain you would see it phrased in this manner. But internal factors versus external factors. And today in this video, I'm going to talk about the internal factors. Now, the way I separate these is, these are the things that you can control, external factors. Okay. This is the internal factors, which is determined by the internal workings, or the bonding, or the internal attractions. That's what a bond is. We've already gone through a chapter on bonding, so we've already talked about different types of bonds. Okay, and for that, I'm just going to be doing some review of this. and recharacterization of it in terms of types of solids. Okay. There are 4 types of solids that we might want to classify. Okay, we have what I would call a molecular, so types of solids. Now these solids are characterized by their bond type. And it is very important to understand when something is a solid, why it's a solid. Well, because it has lots of attraction. But then why does it have lots of attraction? It's because of its bond type. So we have what's called a molecular solid. This is a solid that's held together by covalent bonds. Now, I guess I should say the solid itself is comprised of molecules that are held together by covalent bonds. The actual solid, what holds the molecules together, that's a little different. We have an ionic solid. This is obviously a bond, a substance held together by ionic compounds. Okay, we have what's called a network covalent. Talk about that briefly. And the final one, which we, for the most part, will not discuss in this class, would be a metallic solid. Just out of the scope of this particular class. Okay. So, just take a few moments, and I'm going to run through each one of these just to kind of characterize each individual piece, and that will be just the end of this video here. We have 2 different types of forces that we'll talk about, and the molecular solid will really tend to be characteristic of what's called an intermolecular force. So again, this is for the molecular solids. Okay. I could make an example of a molecule, let's say, let's go with ammonia. Ammonia is NH3. Okay. Its Lewis structure would look like this. Now I'll draw a little more to what I think could be considered proportional to its actual shape. It's got a trigonal planar shape, trigonal pyramidal shape to it. So it's a bit of a nitrogens here, hydrogens, and hydrogens. For this particular substance, ammonia is quite unique. It is actually very highly used in industry. One, it can be used to synthesize all sorts of stuff, but in the refrigeration industry, it's used all the time. It's got a lot of great properties. It is non-toxic to humans, at least, for the most part. It doesn't burn. It's not a very strong oxidizing agent. It's very non-reactive. But for reasons we'll talk about this thing is easily converted between a solid, okay, and a liquid. And there is energy that takes place between this conversion. So let's take a look at why this is so important. I mean, a lot of times nuclear subs will use, a submarine going underneath the water down below needs to have a refrigeration system, and they use ammonia because, well, because of the properties I just mentioned. Either way, liquids, there's a lot of movement with liquids. So they are pretty, liquids, just by the fact that particles are moving around a lot more, they're much more higher energy. Okay. I mean, relative to, say, a solid, which is stationary, okay, for the most part. They're much more slower, therefore they're simply lower energy relative to a liquid. Okay, so when something flips from a liquid to a solid, this is a unique phenomenon. It goes from very fast-moving particles, higher energy, to a slow solid. At some point, going this way, it has to ditch some energy. Okay, it will release heat. So this process is exothermic. Okay, and then coming back to a liquid, obviously it needs to gain energy to go from stationary to moving, and it does that. In this case, it's endothermic. Now, this is from a solid to liquid. This isn't what they use in refrigeration. Refrigeration goes from a liquid to a gas, and conversely, we have the same thing, liquid to a gas. Same exact phenomenon occurs, which is what ammonia does. You could pour ammonia in your skin and evaporate right off, which is a good property for ammonia. As it goes from a gas, again, these are high energy versus some lower energy, relatively speaking, just by some movement. As you go from a liquid to a gas, we need to go from, in this case, add energy to speed them up. Add, okay, or endo, so it would be cold. And then going back would be getting rid of the energy, would be exo, exiting the system. All right, so in a sense, we have this unique property where these particles can flip-flop back and forth. That's why ammonia is pretty important. Okay. Now, why is ammonia? What's unique about ammonia? What's going on with ammonia? So on a molecular level. Okay. It is covalently bound. So the internal bonding. What's going on here? Well, we have a nitrogen molecule bound to a hydrogen, bound to a hydrogen, and bound to a hydrogen. So, and two unbonded pairs there. So, first of all, we have these covalent bonds inside here. Okay, and that holds the actual molecule together. But when we're talking about whether ammonia is going to be a liquid versus a gas, this has nothing to do with the fact of whether it's a liquid or gas. What determines the liquid or gas is that it's called a intramolecular bond. Okay, so we would call this, I misspoke, this, there's two different types of bonding here. We have an intramolecular bond and we have an intermolecular bond. I'll put that one right here. Okay, now in this case, the intramolecular bond is simply the covalent bond. It is, okay, and it, at this point does not affect whether it is a solid, whether it is a liquid, or whether it's a gas. It is holding the framework together of the actual ammonia molecule. Okay, but if I want to know whether something's liquid or gas, I got to know, okay, based on this little ammonia molecule, how well does it stick to other ammonia molecules? And then that ultimately is going to be what we're talking about here. This is not the covalent bond. This is called the intermolecular bond. This is the between molecule bonding. What is the attraction between these things? Of course, there is only one attraction in chemistry, and that is the positive versus negative attraction of Coulomb's law. Okay, so at some point there has to be some amount of positive and negative attraction here. We've already discussed this, intermolecular bonding, polar molecules. So at this point, at some way, somehow, the nitrogen has some intermolecular attractions between the two. Okay. This is called what I would refer to as hydrogen bonding. So our first intermolecular bond I'll discuss here is hydrogen bonding. This is where we have a highly electronegative atom, I'll call it X, bound to some other highly electronegative atom, and the electrons being shared are not being shared so equally, and they will be dragged over to the highly electronegative atom. Now, for this atom, I would say nitrogen, oxygen, fluorine, sometimes chlorine can be included in there as well. All right, these guys are the big guys. Anytime you have one of these guys bound to some other atom, we'll have an unusual amount of attraction dragged over towards, for the electrons to be dragged over towards that highly electronegative atom. So in this case, I have the nitrogen, and I have these hydrogen atoms, and the nitrogen is drawing the electrons towards the nitrogen, making it negative, and these guys are relatively positive. I will also say that, as we've learned previously, that there is an issue of not only electronegativity, so this is creating what we call a polar bond, okay, but we also have the idea of symmetry. Balanced electrically someplace, will one side be negative, one side be positive? Okay, we need to have an asymmetricalness to this molecule. We've already looked at the number of shapes that this thing will form, and this particular PowerPoint will not go into all those details. If you want to, you can go back and look later, but this is an asymmetrical molecule as opposed to something maybe like this, where we have a negative, or let's say a positive center, negative, 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 where I don't have a region of negative, region of positive. Okay, so our main intermolecular force that we'll look for between molecules is called a hydrogen bonding. Now there are others, variations of this, but this is the one that we're going to be focusing on for this particular class. Okay. We have intra, which is the covalent bond, and inter, which is the between molecules. Now again, the fact that it's covalently bound means we have these molecules. That's a little bit unique, which therefore means we have internal covalence and we have these external little intermolecular forces. These forces are what are going to govern whether it's a solid, liquid, or gas. If there's no intermolecular forces, it will be a gas. If there's minimal amount of intermolecular forces, it will be a liquid. If there's lots of them, kick it over to a solid. So to recap the covalent compounds before we get into ionic, we have a few unique things about covalence is they have molecules, unique units. They have intermolecular force between them, that this intermolecular force can vary dramatically. So with the covalent compounds, we have the ability to be a solid, a liquid, and a gas. This is unique to molecules. Solids, liquids, and gases. So I would expect water, okay, H2O, to be the ability to do solids, liquids, and gases. I would expect carbon dioxide, even though not as much. It's present as gas. This could be liquid. We've seen dry ice, solid, carbon dioxide. Okay. Now, for an ionic compound, okay, a little bit different setup. We have a cation and we have an anion. Cation, anion, and it forms what we call a crystalline solid. This is unique to ionic compounds, and I'll just draw a couple more of these out. We've already talked about the ionic crystal in bonding. I'm not going to go through all of the properties of this thing, but inherently, as opposed to this crystal, okay, the ionic crystal, of course crystals are essentially solid, so there's a unique or a very different setup to an ionic substance versus a molecular substance. Now, for an ionic substance, I'm going to extend the page here a moment. Okay, now for an ionic substance, is there this idea of an internal or again internal versus inter versus intra? I should say intra versus inter. Not really. Okay, when I melt, this is a very important idea, is that when I go through the melting process, am I breaking a covalent bond? Absolutely not. When I go from a solid to liquid or liquid to gas, Okay, I'm overcoming the intermolecular forces. Very important to understand. Okay. Do these intermolecular forces exist in ionic compounds? Not really. Okay. What's holding together an ionic compound? Or if I melt an ionic compound, not very well written in compound. Okay. What's actually happening here? Okay. Well, we'll talk more about temperature in a minute or later on, but essentially, temperature is movement. Okay, so these things start shaking back and forth. This guy starts shaking back and forth, and there is an attraction right here, right here, right here, right here. And these attractions here are essentially the ionic bond. So the whole thing is held together by an ionic bond. There's no intermolecular forces. There's no intramolecular forces. The only force we have here is the ionic bond. So when you melt an ionic bond, you're actually breaking the ionic bond. This is going to drive the melting points up extremely high. This is a very strong bond. Okay, so because it's so strong, we have it holding together. This thing, in all intents and purposes, is going to be solid. We talked about the factors that affect the melting points of these guys, which are going to be, I'm going to put that right here. This is review. Affecting melting points of ionic. Okay, that's going to be difference of charge. Got messed up. Difference of charge and radius. All of this is referring to Coulomb's law. Now, again, that's not the topic of this video, but that's just what it is. So in this case, it's very important to understand that these bonds are extremely strong relative to some intermolecular forces. I would say that for a molecule, this intra-covalent bond, extremely strong, stronger than the ionic bond. But that's not what's holding things together here. That's not what's holding the solid, liquid, and gas together. It's this intermolecular bond right here, okay, which is, to this point, all we discuss is the hydrogen bonding. Here, ionic bond is actually being melted. Our last type of solid that I'm going to talk about here, and the factors, the internal factors, and I'll just start a new page here, and we'll call it the network covalent. The network covalent is very much similar to the ionic. It forms a crystal, but rather than having ionic bonds connecting everything together, it is going to be connected by covalent bonds. Okay, so an example of this is a diamond. Very hard substance. Why? Because of the interwebbing, and you have carbons, and it's carbon bonds 4 times, so it forms very unique patterns, which is why diamonds have their shapes. They chip or they break diamonds along these patterns, break lines, and a person who's a gemologist would be able to break these things and do different things with diamonds, but they're very, very, very hard. Okay, you should understand that of the compounds that can do this type of bonding are very few. The carbon family is essentially the only ones. Carbon, silicon, and germanium are the only ones that can do this type of bonding. Okay, so if we were to look at this substance, you would fully expect, once again, this to be a solid, not a liquid, not a gas. Could it be would be temperatures in excess of 3,000 degrees Celsius. So on Earth, solids only. For ionic compounds, solids only. You should understand why, because of how the bond's set up. Covalent molecules in solids, liquids, and gases, and you should understand why. Thank you very much.